To begin our study of Kepler's laws of planetary motion, we'll start with, who were these people who came up with the laws, and what are they, and then we'll get into the proof of the first law. Johannes Kepler was a German astronomer, lived in the 1571 to 1630, and he had actually worked under another astronomer, Tycho Brahe, who was a Danish astronomer, a nobleman who actually owned an island and created a research institute. And what Tycho did is he had, in his research institute, he actually did very, very minute calculations of observations, I should say, of positions of the stars and the planets. Very, very detailed. I mean, incredibly detailed. And the precision was phenomenal. And so, as an assistant to Tycho, Kepler had access to this information, and later went and looked at, the locations of where the planets were, and came up with some observations which, again, you think about, boy, no computers, no calculators. To notice some of the things that he noticed are incredible. So let me show you what he came up with for these laws. Okay, the first law of planetary motion is known as the law of orbits. And what he noticed is that all the planets moved in elliptical orbits around the sun, and the sun was at a focus. And so we're saying mathematically precise ellipse, and the sun is at that mathematical point, we call the focus. So having studied ellipses before, we're going to be able to use that information to make some connections. Let me illustrate what that law kind of looks like. So we have this orbit of a planet along this ellipse. Sun is indicating at a focus here. And just to remind you some things about ellipses then, we have something called eccentricity or eccentricity, depending how you want to pronounce it, this E thing. And that sort of describes the stretchiness of the ellipse from a circle. So a circle has eccentricity of 0, and then as eccentricity approaches a value of 1, the ellipse stretches further and further out. Now, this particular drawing here is quite exaggerated because most planets, although they, are in elliptical shapes, they're actually pretty close to looking like circles for the most part, okay? Pluto, whether you want to call it a planet or not, it also follows, the orbital mechanics here. That's the most stretched out one. Mercury's a little bit stretched out. But this also applies for comets, which definitely have very high eccentricities, okay? Let's show you a little example here. So here we can, we've got our sun, you can read this information up here. So we're going to put a planet on here and give it some initial velocity and send it on its way. And we can watch sort of the orbit that's created from this. And this one, has a little bit of a eccentricity, a little bit off from being a circle, because the sun is not at the center, which it would be in a perfect circle, right? We can play around with this. I'll make sure to include this link on the website also. Well, let's see. Let's shoot it off that way, see what happens. Okay, that's going to have a much wider orbit. Let's probably go off a little bit off the screen. But it should come back eventually. Do we wait for it? What? Why not? Here it comes. But it should connect back up again. So we're always going to have these orbits connecting back up. Whoa, it missed. I guess this one's not going to quite stay in orbit. That's kind of interesting. You can also do some other things like try to send it off the other direction and watch the gravitational force pull it in. Oh, crash! I'll make sure to link it. I know you'll want to crash some planets. So that's the first law. Looking at sort of an illustration here, you can kind of see the ellipse nature of the orbits of the planets and with their eccentricities. But again, let me point out that for our planets in our solar system, the eccentricities are actually pretty close to zero for the most part. The highest value is 0.25 for Pluto and Mercury at a 0.206. Looking at this illustration, here's an ellipse with an eccentricity of 0.23. You just glance at that. If you weren't told it's not a circle, you'd probably say it was a circle. So for the most part, these aren't really strong ellipses for planets in our solar system. But again, this applies to comets and asteroids and other things as well, which would have more elliptical things. Okay, so that's what it looks like. Kepler's second law then is the law of areas. And it says a line connecting a planet to the sun sweeps out equal areas in equal times. What does that mean? Well, this applet here will allow us to look at this idea of sweeping out equal areas in equal times as we've got this planet moving around a sun here. This one's actually a perfect circle, saying that, okay, over a certain amount of time it's just, shading, these equal areas in equal times, as you see. Okay, so each region, black and yellow, is same area for the same amount of time. Now, what we're going to do here is we're going to increase the eccentricity because it's not really surprising with the circle. So, we'll warp this. Let's go to this value. So here we're still going to be moving equal areas in equal times. Now, what's that red vector indicating? That's indicating the velocity of the planet. Okay, so that's our velocity vector. So as you see, to be able to have equal areas in equal times, it means when the planet is close to the sun, it has to move much, much quicker than when it's farther from the sun so that it can sweep out this equal area for the same amount of time. Okay, so we have to speed up in those cases. Moving to some values in here, same idea. So a little less dramatic than the last example, but it's going a little faster here and then a little slower when it gets further from the sun. Kepler's third law of planetary motion is that the square of the period, in other words, how much time it takes for the planet to go around the sun once, so the square of that is proportional to the cube of the semi-major axis of the orbit. Okay, well, what are we talking about there? The semi-major axis of the orbit, if you recall, the semi-major axis for an ellipse is just, half of that distance across the major axis, across the center there. This is really a data analysis thing, just doing a best fit kind of data curve here. In this particular example, they were taking the square of the orbital periods. Okay, so this is the number of years squared for each planet to go around the sun. Okay, in Earth years, and the cube of the semi-major axis. And by plotting those two values, you end up getting a straight line. Okay, which means you get the proportionality between, as I said, the period squared, indicating the t there, t squared, and a cubed is that length of the semi-major axis cubed. And then the slope of this line is that proportionality constant, turns out to be 4 pi squared over gm, where g is the universal gravitation constant and m is the mass, I think, of the planet. Oops, sorry, I meant m is the mass of the sun, not the planet. And, we could talk about this orbital mechanics then also applying for planets going around other stars, using those masses of those stars. So that's what Kepler's laws are. Now we're going to go into proving some of this. Again, Kepler did this all by observation. It's called the scientific laws because it's what he noticed. It seemed to always be true. It's not a proof. Sir Isaac Newton proved Kepler's laws of planetary motion, and this was published in his famous works, the most famous work that Newton did, known as the Principia in Latin, in 1687. The English version of this would be called Mathematical Principles of Natural Philosophy. And yes, Newton was English, but in those days you published academic works in the Latin language. So anyway, so that's where Newton printed this material of proofs of Kepler's laws. So really, he changed them from being laws to mathematical theorems, essentially. And really, the only two things that we need to use to make these proofs, starting points, we do have two premises. And these are Newton's laws themselves. Newton's laws of planetary motion. Newton's second law of motion. Didn't need to say planetary motion, actually. Just Newton's law of motion that, F equals ma, everybody's familiar with. In this particular case, notice I've written it in vector form, right? The acceleration of an object is proportional to the force applied, both in terms of direction and magnitude here. And the other law is Newton's law of universal gravitation. And the law of universal gravitation, if you know this one, and actually you've encountered it before, certainly in Calc 2 this was brought up, the inverse square law for gravity, so that the magnitude of the force is proportional to 1 over the distance squared. Now we've got these two different ways of writing this that I just want to clarify. And actually we dealt with this a little bit in class before. This doesn't look like inverse squared, it looks like inverse cubed, but that's because we've got, this is the vector between the two objects, right? And so, in this form I changed it so it looks more like the familiar inverse square law, where u is in fact just the unit vector. I can clarify some of that down here, okay? Right, so our force vector, little m and big M are the masses of the planet and the sun, or actually can be the masses of any two objects gravitationally, but in this case it's planet and the sun. Big G is the gravitation constant. In this case, the sort of fancy R is the magnitude of the vector between the two objects. And then finally, as I said, the U vector is the unit vector in the direction of the R, which is what corrects for the two different notations. And we'll use both forms of this when we go through the proof. But Newton's proof of Kepler's laws of planetary motion require only these two laws themselves, okay? And so that's what we're going to use along with understanding of some vector stuff. So we need to, first of all, look at, a diagram of what's going on here. The vectors here, we've got our planet orbiting around the sun. We've got a velocity vector indicating the velocity here. We know that our position vector is going to go straight from the sun out to the planet because we're going to put the sun at the origin, actually, for this particular situation. It's going to work out best for us. So this becomes the position vector of the planet, describing the motion. And then our acceleration vector, we know, is directly in line with back to the sun because, of course, that's the direction that the gravity is pulling it in. And then just keep a reminder here that the velocity vector is, of course, the derivative of our position vector, and the acceleration being the second derivative of the position vector. So, these relationships are going to be important here. All right, so to show the motion of the planets is in the plane is the first step we're going to do to prove this first law. Remember, the first law is that the planets are orbiting in elliptic orbit. And so the first thing is actually to show that the motion is in fact planar. It's in a single plane, okay? And the first thing to do is we're going to have to equate these two Newton's laws that we said we're going to use, the gravitation law and Newton's second law of motion. Okay, so equating Newton's two laws together, we're literally going to set them equal to each other here. And then the first thing that we see is the mass of the planet is completely irrelevant to the whole thing. That just cancels out. And then we can say then the acceleration due to gravity is just equal to the stuff that's left over on the other side. All right, let's see, over r cubed and our r vector. Now, this is meaning that the acceleration and the position vector are proportional. And notice the negative in front, of course, that's indicating that, in fact, they are in opposite direction, but parallel, which agrees completely with the drawing that we have here, right? So that agrees that way. Oops, need a writing tool. Here we go. So we've got acceleration, then we can say is parallel to the position vector, right? And then we said, in particular, it's also opposite, okay? But vector-wise, that means that these two things, if we go to a cross product, the cross product of these two is 0, the 0 vector, okay? So we have the 0 vector is the cross product. Well, if you keep in mind here that this cross product 0, we're going to actually take a derivative that at first is going to seem like comes out of nowhere, but you'll see that it's going to get used in a little bit. We're actually going to take the derivative of the cross product of our position vector and the velocity vector, okay? And this requires a product rule, right? So derivative of position vector cross velocity vector plus position vector crossed with the derivative of the velocity vector. Of course, r prime is the velocity vector, so this just ends up being v cross v, and here v prime is the acceleration vector. All right. And now we've got, look at that, r cross a, which we know is the 0 vector. We also have v cross v, but v cross v is a vector crossed with itself, so that's also the 0 vector. So putting these together, we just get the 0 vector. So why did we even bother doing this? Well, the key to this, taking this derivative of r cross v being the 0 vector, for something, a derivative of something to be 0 means the original thing had to have been constant, right? So, in fact, r cross v is a constant vector. And that's the reason we actually did this cross product, was to show that. Let's call this something. Let's call this resulting vector, we'll call it h. Okay, you may say, why h? Just because the notes I wrote up, I called it h, for lack of anything else. Okay, so we'll have to keep in mind when this h thing, we're going to use it, we'll use the fact that it's constant. That'll be useful. Okay. The other thing with h being constant, not being constant, but just h being a cross product of both r and v, that means that the h vector has to be perpendicular to both of these vectors, right? So h has to be perpendicular. In particular, I want to point out it's perpendicular to our position vector. Now, our position vector, though, as the planet's orbiting the sun, the position vector actually changes for various points in time. So not only is it perpendicular to r, it's always perpendicular to r. So you want to think of that as that vector function. It's always perpendicular. Okay. So, going back, thinking about cross product and right-hand rule, r cross v with a right-hand rule actually means that this constant vector h is coming out of the screen towards us. Okay, so that's something to keep in mind, that it's actually out of that plane of the screen. Okay, and that's true for all values of t, meaning that the planet must lie in the plane through the origin perpendicular to h. So we've achieved that goal now, showing the planet's always in the same plane. Now that we've shown that a planet's orbit always remains in a single plane, now we'll show that within that plane the path is an ellipse. Okay, and we're going to start out with this. constant h vector, which we had at the last video, being position vector crossed with the velocity vector. So remember, that's a constant vector coming straight out of the screen towards us here. And we're going to do a rewrite on the velocity vector and just say, well, remember, velocity vector, is in fact the derivative of position. All right, so we're going to have r cross r prime. And then we're going to rewrite our position vector this way. And we're going to think about, well, the position vector is the magnitude of the position vector scalar multiplied with the unit vector in the same direction, right? So, on our diagram, we can have this unit vector, same direction as r, just scaled to unit length 1, multiply that by the magnitude of r, and you get the r vector back, okay? So that's going to have us rewrite this entire thing as magnitude of r times unit vector, that's scalar times, cross product with magnitude of r, scalar multiplied by the unit vector, and it's the derivative of that, okay? Now, both the magnitude and the direction, okay, they're both functions of time that change as the planet orbits around the sun. And because of that, to actually take the derivative of this product, we have to use a product rule, okay? So this first term, we still have r times unit vector, and crossed with, here's our product rule, the derivative of r, scalar multiplied with the unit vector, plus r times the derivative of the unit vector. And now what we do is we're going to distribute this cross product over addition, okay? Cross products distribute. You just have to make sure you keep things in the exact same order, because cross products are not commutative. So we're going to have r times u cross product with r prime u plus ru crossed with ru prime. Okay. So although cross products are not commutative, we have the scalar multiplications taking place in here, okay? The r's and the r primes. And in fact, those can come up front because they're scalar multiplied. So we're going to have r times r prime. That's just, because these are scalars, they're scalar functions, but it's regular multiplication for scalar functions then. And that result gets scalar multiplied by u cross u. And likewise, with the second term here, we're going to have r times r, and that gets scalar multiplied by u cross u prime. Now, we have a u cross u, a vector cross with itself. Of course, that gets us the zero vector. And so we can have an end result here that we get r squared scalar multiplied by u cross u prime. All right. And so that's what our h vector is. So now we're going to take the cross product of the acceleration vector and the constant h vector. Now, good question to ask is, why would you do this? Well, Newton thought of it. I didn't. So give Newton credit for coming up with this, because that was sort of the inspired piece here. So in doing this a cross h, first of all, we're going to rewrite the acceleration vector, back to what we came up with before, that the acceleration vector was proportional to the position vector. And in fact, rewriting it sort of in the more familiar way here with the unit vector, gm over r squared times the unit vector. We'll plug this in for the acceleration vector. All right, so we're going to take this cross product of a cross h. So here's our acceleration vector. There's the a. And then we're going to take a cross product of that with the h vector, and actually we're going to replace that with the r squared scalar multiplied with u cross u prime. So it's all of that. All right. So we get all of that stuff now. So now look at this here. We have r squared and r squared that cancel out. So that's kind of neat. And then we're just left with this negative big GM out front, along with u crossed with, parentheses, u crossed with u prime. All right, so now we're going to try to figure out what is this u crossed with u prime simplify to. About this cross product here. First of all, let's think about what's this u vector doing. Remember, this is the unit vector pointing in the direction from the sun to the planet. The way we drew it, the planet was going counterclockwise around the sun. So a unit vector, though, traveling counterclockwise is always going to be pointing to the endpoint being on a unit circle, right? It would just be going around this way. Speed would change, right? The rate at which it goes around changes, but it keeps going this way. So what does u prime look like? Well, u prime is going to be then, the derivative of this u vector. Well, in other words, it's going to be a velocity vector for this thing, for the u vector, okay? Not the velocity of the planet, just the velocity vector for this u vector here. Well, that's got to be moving in the direction perpendicular, or I'm sorry, in the direction of the motion, which is perpendicular then to the u vector, because the u vector ends up being a radius for the unit circle. And so then we've got to have the u prime vector tangent to the circle, and the only way to do that is through perpendicular. So u and u prime are perpendicular. So to do this cross product now, in the parentheses u cross u prime, well, first of all, any vector is the same, so we can take the u vector and we can just slide it out here. So we've got the two tails, u and u prime, tail to tail. Now this is interactive part of the video. You've got to do your right-hand rule onto the screen. U cross u prime, your right-hand rule should be, your thumb should be pointing at you out of the screen, okay? So that inner cross product that we have here, this is out of the screen, right? Or another way of saying it, it's out of the direction, or out of the plane that the planet's moving in, okay? And so now what's u here cross this new vector out of the screen going to be? Well, that's going to be another right-hand rule you're going to have to do. Line up your right hand, u cross with this vector coming out of the screen. Well, that should be a vector pointing on this picture up and to the right. In fact, it's got to be exactly the opposite direction of the u prime vector we have on here. It should be right here. Move that out of the way. Okay, so it's right there. That's what that vector is. Now it has to be a unit length vector, because everything we're doing here is unit length, and as you cross product a bunch of unit length vectors, they give you unit length vectors. Okay, so this whole thing that we just did turns out to simplify to be negative u prime. So we'll plug that into the work we were doing up here, right? And so we get this to be negative gm times negative u prime. So we can now conclude here that our a cross h vector is just going to be a cross h equals this, well, now the negative times the negative makes a positive, gm u prime. Okay, now we're going to take the velocity vector crossed with that constant h vector, and we're going to take the derivative of that cross product. Why, you would ask? Again, this is one of these Newton-inspired ideas. I don't know why, but it's going to work. So that's why we're going to use it. Okay, so because the velocity, well, taking these two vectors, what we'll do is we're just going to use a product rule on this, okay? And in doing the product rule, we're going to get, v prime cross h plus v cross h prime. Now, if you remember, h itself was constant, right? And so if h was constant, what's h prime going to be? Did you say it? It's going to be the zero vector, right? And so v cross of the zero vector is a zero vector. The other thing we're going to look at is, hey, here's the derivative of velocity. Derivative of velocity, that's acceleration. So all we have left from this then is this ends up being acceleration crossed with h. Now, where do we see that? Well, the end of the last video, we just had acceleration vector cross h was just that gravitation constant times mass of the sun times u prime. So what we now have are these two pieces being equal now, right? Now, this itself is a differential equation. Now, why is this a differential equation? Well, we have the derivative of this stuff equals a constant times the derivative of u. You know, if you want, you could say, and remember, this is the derivative with respect to time. Another way of writing this, derivative of v cross h, like that, is equal to the derivative with respect to time of gm u, right? Gm as constant can be pulled up front, but otherwise that doesn't really matter. And so, hey, if these two derivatives are equal, then of course that means v cross h must be the same except they're off by a constant, right? You're taking the antiderivative of both sides, really. So this is equal to gmu. Sorry, this one up here was supposed to be u prime. Oh, no, it wasn't. Derivative. And then plus we have to have a constant of integration, right, for solving a differential equation. So where does that lead us? Well, that gets us into this picture. Let me pull up. Actually, before I show this picture, let me show you how I want to set this up first. Because v cross h, okay, cross product here. Cross product we know has to be perpendicular to both of its terms. So the cross product is certainly perpendicular to this constant vector h. Now we'd already determined h was perpendicular to the plane of orbit, and therefore h has to be perpendicular to u, right? Now, if h is perpendicular to u and to v cross h, both at the same time, and looking at the equation we have here, that's actually saying, oh, the only way for this to work out is if this constant vector of integration, okay, has to be in the plane of orbit, right? So it's in the plane of orbit, and we're going to set this up so that the plane of orbit, we'll call this plane of orbit in the xy plane, all right? And so that's going to help set up this thing. We're also going to set up coordinates. So we're going to set up our coordinate axes here so that we have the h vector is going to be parallel to our standard unit vector in the z-axis direction. And let's set up then the c vector parallel to the standard I vector, in other words, the x-axis. Okay, we've now set up our coordinate system here. Sun is still at the origin. Prior to this, we only said origin, and we're thinking of a plane, but now we're going into the xyz axis. And we set it up so that the z-axis was going to be aligned with this constant h vector we've been working with on this whole proof. And then we also had this constant of integration we just came up with, this c constant, and that's in the xy plane. It's in the plane of orbit, and we're going to line this up along the x-axis. After all, we can set up the x-axis any way we want. We're choosing to do it this way, okay? And so then our r vector, right? Here's the orbit of the planet shown here, and the r vector points to the planet itself. And what we're going to do is we're going to set up an angle theta. And the angle theta then is going to be between the planet position vector r and the constant c vector. So in other words, this right here, that's theta. And so by talking about, okay, we've got an angle theta from the x-axis, and we've got a position vector r, that gives us the coordinates of the planet to be r, comma, theta, where r is in fact, the magnitude of the position vector, just like it always has been, and then theta is the angle from the x-axis. So what we've done is we've now set the orbit of the planet in polar coordinates. All right? So the orbit of the planet is purely in polar coordinates. Now with that in mind, we're going to do another one of these, not my idea, but a Newton-inspired idea, of taking r dot v cross h. Again, not something you would just think of off the top of your head, I don't think. So we're doing this dot product position vector dotted with the cross product of v cross h. Okay. Now, remind you that in the last video, this v cross h vector we found to be gmu plus that c constant vector. So we're going to plug that in here and rewrite this then as r dot this new stuff gmu plus the constant vector. Okay, and now we'll distribute the dot product here. So we'll go, r dot gmu plus r dot c. Okay, so we have r dot gmu, g and m are constants. We'll just pull those up front. So we get gm scalar multiplied by r dot u plus r dot c. Okay, and rewrite with some of the other information we have here. We know r, the r position vector, is just the magnitude of r, little r, times the unit vector. So that's this r value dotted with u. You might see where we're going with that one. Maybe a little less obvious is what we're going to do next with the r dot c. R dot c, if you look at that, you're saying, okay, you've got a dot product between two vectors whose angle we know. We're going to use the definition of dot product. Okay, definition of dot product says, oh, it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Right, that's definition. So, a couple things we can simplify now. First of all, u dot u, you're taking a unit vector dotted with itself. It's 1. Nice. And so let's just rewrite this. We now have gm r plus magnitude of r plus times the magnitude of c times the cosine of theta. All right, we need to take a little aside to prove a particular vector property here that, in general, vector A dot cross product of vectors B and C is the same as A cross B dotted with C. Okay, and in this proof, I'm going to break out, vectors A, B, and C into these components with the subscripts x, y, and z. So I'll start with this left side here, A dot B cross C, and we'll start rewriting this in terms of the components that we wrote up here. So the A, A sub x, A sub y, A sub z, okay, is going to be dotted with the cross product. Now the cross product being all this lovely stuff. You can look up the formula if you need to, but it's, by cz minus bz cy, comma, bz cx, oops, that should be the x, minus bx cz, comma, bx cy minus by, cz. Made that all fit. Great. So now we're going to do this lovely dot product here. So we have ax, and I'll just multiply it by that first term, by cz minus bz cy. Okay, plus the next term, ay times bz cx minus bx cz. Getting a little hard to read my writing here, plus az times bx cy minus by cz. All right. Now this stuff can actually all be written as a determinant here. So let me rewrite this as a determinant as ax. Maybe you can see this here, right? The ax is being multiplied by by cz minus bz cy. Do you see how that works in a 3 by 3 determinant? Oops, that's a little sloppy here. Gotta rewrite that. That was the bz, and this is cy, cz. So just that part of the determinant gets that first term here. Likewise with the second one, the ay goes here. It's ay times bz times cx minus ay times bx times cz, and then likewise the last one. Okay. So it turns out that this a dot b cross c is this 3 by 3 determinant, which is actually kind of a neat setup. But you can also dissect this determinant another way. We could dissect it, or if we start multiplying it out here, we could say, look, it's going to be this cx term times, ay times bz times cx minus az times by times cx, in that sort of a manner. And then approaching it that way, sort of factoring out a little bit, we get ay bz minus az by, sounds a little crazy, and all that times the cx. And likewise we can do it for the other terms, factor out a cy for its terms, and we get az bx minus ax bz times cy, and likewise the last set, ax by minus ay bx times cz. Well, that can be written then, all that stuff factored out, as an, az by minus ay bz. Yeah, you can work the rest of these out. Right, the rest of those dotted with cx, cy, cz. Sorry, getting a little sloppy. But that's just saying, oh, this first thing ends up just being vector A cross vector B, and all that dotted with vector C, which is what we wanted. Okay, back to, we need to show that R dot V cross H is the magnitude of H squared. Okay, and so to do that, we're going to use the fact that we just proved that we can sort of reorder this dot cross product combo. And so by using this, that means the R dot V cross H is in fact the same as taking R cross V and taking that result and dotting that with H. Okay? Now, when we initially worked with R cross V, and in fact that's how we defined H, right? That was the original definition of H. And so we're going to plug that in for here, and that, of course, just means we get H dot H, right? Well, what is H dot H? H dot H is the magnitude of H squared. So in fact, we've proven that. Okay. So now what we'll do with this is, we've got this form here, but we also came up with earlier this version of r dot v cross h. So that means all of this stuff is also equal to the magnitude of h squared. Okay, so we've got h squared equals this stuff. In fact, let me replace the magnitude of vector r with, in fact, magnitude of r is r, right? So both these terms have r in it, so we'll factor this r out, and we're left with gm plus the magnitude of that constant vector c times the cosine of theta. And that's equal to magnitude of h squared. So solving this for r is going to be the magnitude of vector h squared over g times m plus the magnitude of vector c times the cosine of theta. And I'm going to take that on just a little bit of a rewrite again. So I'm going to, just a second here. Okay, we're going to factor out of the denominator a gm, so it reads 1 plus the magnitude of c over gm times the cosine of theta. A little odd, I know. And then on the numerator we still have this magnitude of vector h squared. And in fact, I'm going to rewrite it as two separate fractions that way. And then I'm going to define couple of things here. I'm going to let E be the magnitude of vector c over gm. All right. And we're going to let D be the magnitude of vector h squared over the magnitude of vector c. Okay. Now, by doing this, note that this part in here, that just becomes the E. And this part here is actually E times D, right? So we can write the whole final thing then, R is equal to E times D divided by 1 plus E times the cosine of theta. Now, I claim what we have here is a big deal. R equals ED times 1 plus E cosine theta. This is sort of the happy end of this lecture. You may say, well, wait a minute, that hasn't shown we have an elliptical orbit. And I claim it does. But I'm leaving a little bit to you, and this will be your assignment in special problems. You're going to have to show that, in fact, that is the equation of an ellipse in polar coordinates. So, thanks for watching. Enjoy your proof.